Welcome to qnawire.
Alright, let's go ahead and solve this problem. We're given f, which is y comma z minus y comma x, and S is the region that is forming a tetrahedron with the vertices located at the origin. 1, 0, 0, 0, 1, 0, and 0, 0, 1 is drawn below right here. And as usual, we're just going to find the flux through S by evaluating each of the flux through I1, I2, I3, I4, which are the four surfaces that we can see right here. All right, so let's start with I1. The normal vector is the one that heading towards the negative x direction on the yz plane, so we know that it is negative 1, comma 0, comma 0, which means that f dot n is equal to negative y. Now, we know that the value of x is equal to 0, and then we also know that the integration is going to go through all of the y's and all of the z's. So I'm going to say y goes from 0 to 1. We have to be a little bit careful with the z because it goes from this to there. It has to go through one equation to another, where one is y is equal to 0, and the other is y plus z is equal to 1. So z itself goes through 1 minus y. So that part, I want you to be a little bit careful. So 0, 1 minus y. Okay, and then we evaluate negative y, dz, dy. Okay, the calculation is quite straightforward. I'll let you do that part. You will end up having negative 1 over 6. Okay, now let's move on to I2. I2 is the one that goes downwards in the z direction, so the normal vector is equal to 0, comma 0, comma negative 1, which makes the dot product equal to negative x. Z is equal to 0, and the flux integral that we're going to calculate is going to go from the x values of 0 to 1, and you will find that it's exactly the same notation, it's just different variables. The value of the y goes from 0 to 1 minus x. This is negative x dy dx, so you will get negative 1/6 again. I3. It would be nice if I could say that it's symmetric, it's the same kind of situation. Numerically, you will end up having the same thing, but this one, the expression is slightly different, so I will go through this. The normal vector is towards the negative y-axis direction, so it's 0, negative 1, comma 0, making the dot product equal to y minus z. Now, a little bit that we need to keep in mind here is that y is equal to 0 on this plane, on the xz plane. So we know that this is actually negative z. And then we can say that we can probably get the same kind of integration. Do we? Let's check. The z values changes from 0 to 1. The x changes from z is equal to 0 to 1 minus z. So indeed, we do get the same expression, dx dz. This is negative 1/6. Okay, I4. Now this is the one that's coming towards us, it's going to be the normal line of the plane x plus y plus z equals to 1. If you want to remember why that would be the plane right here, then I would like you to refer back to a couple of chapters before when we talked about surfaces of finding the equations of planes. Anyhow, we know that the normal line, the normal vector is going to be 1, 1, 1, partially because we know that the equation of the plane is x plus y plus z is equal to 1. F dot n, therefore, equals y plus z minus y plus x. Okay, we can see that the y's cancel each other, and you want to get rid of z right here and express it in terms of x and y because of the next integration. However, we know that x plus y plus z is equal to 1, so z can be expressed as 1 minus x minus y. So a y comes back, but now the x cancels each other, so we will get 1 minus y. So the integration, the y value changes from 0 to 1, the x value changes from 0 to 1 minus y, similar to the previous setup. It's just that the integration is 1 minus y instead of negative y. This, when you evaluate it, you will get positive 1/3. So let's summarize this. Let me make this a little smaller. Okay, we have 3 fluxes, identical values, negative 1/6 and a positive 1/3. That's the diagonal flux due to the I4. So we know the total flux is equal to 1/3 minus 3 times 1/6, and that is equal to negative 1/6. And that is how you solve this problem.